Yes, sir.
Okay. Okay, so maybe we start. So we are discussing about the heat equations, no? Ut minus Laplace is equal to say 0 in Rn, T is positive, and U is equal to G on Rn. Then what we have seen that if my G, which is continuous on Rn and then bounded in Rn, actually we don't need the boundedness, but we need that solution should be bounded, and that is why we have seen that I need G is bounded. And then this problem has a solutions of this form. Oh, sorry. Okay, so here P is here fundamental solutions of your heat equation. So one thing you notice that if my G is greater or equal to 0, okay, if G is my greater or equal to 0, then U over xt is always positive for any time x and t. What I'm saying that, okay, so G is not identically 0. Okay, if G is not identically 0 and if G is not negative, then my solution uxt to this Cauchy problem or the global Cauchy problem, it is always positive. Is it not? So this is sometimes called the infinite speed of propagations of heat equations. That means if you start with say non-negative initial value, then at any time and space point your solution is positive. So this kind of the infinite speed of propagation. Okay, that is just one remark I know made it. So today I'll talk about like a maximum principle and then kind of uniqueness result. So we have seen the maximum principle for Laplace equation. So what it says that if you consider the bounded domain and if you is a harmonic function on that domain, then the maximum attains in the boundary. So similar kind of result we may expect here. So for that, what I need, so I'm defining my omega, which is again subset of Rn. This is open and bounded domain in Rn, and say suppose my t is greater than 0, which is fixed. Okay, so I'm saying that parabolic cylinder how it is. This is I denote by omega t. This is nothing but my omega cos 0t. Okay, so you can consider closed t or open t, that does not matter. You can consider the open t also. And the parabolic boundary we denote as gamma t. This is nothing but if you consider omega t closure difference of omega t. In particular, it looks like, so this is my say omega. Okay, so similarly you can have, so what it says that this top capital T is not included. This one, this is the boundary of del omega. Okay, this part, this is this one is your omega, then this part, and then this one. It included this 0, but not the top one. So this is the boundary, gamma t. This is called the parabolic boundary. Parabolic boundary of omega t. Okay. So that means.
Can you again explain once again that what top part is not included?
No. See, I'm saying that you have omega cross 0 to t.
Yes, sir.
Okay. So that means this is my top, no? Because this one is nothing but omega. If you consider omega cross that t, is it not? So here the points like this. So this is your omega, and then capital T means this is x and t. These are the points. Okay, where x is belongs to your omega. Is it not? These are the points, but this is not included. That at point capital T, this is not included, but this one is included. This boundary is included only. Okay, that means basically it is dole omega or t is equal to 0. See, this is your omega. Okay, open bounded domain. So the boundary is basically my this omega, this one, and then I am including this point and then this one. Okay, but not my top capital T, not this part. See, if we just give you something like that, what are the boundary point? You will say that okay, these are the boundary, these, and then these also boundary.
Yes, sir.
So this is not included. Only this one, and this one. Okay, this top is not included. So that is actually the omega t closure, difference omega of t.
Then sir, why are we calling it as parabolic?
It's look like it's cylindrical. It's why it is called parabolic. That is generally the convention. People are saying that it's called the parabolic boundary. Okay, the top is not included. So cylindrical, it is basically there looks like a cylinder because omega cross 0 of t, it is a cylinder. So why it is parabolic? It looks like something like that, no? That kind of U form. Is it not? It's kind of looks like a paraboloid, no?
Yeah.
So it is not included, but if this one is included, it looks like a paraboloid kind of things. But anyway, it's just the conventions people are using that it's called the parabolic boundary. So maybe this is, I'm just interpreting in this way, but it may not be the case, but it seems that because of that they are saying that it's a parabolic boundary. This is your omega t, which is the parabolic cylinder, and then this is the boundary. So what I try to say is the following, that if you have maximum principle for the heat equation means basically suppose I have a solution U which is C21 of omega t intersection C of omega t closure. Okay, so omega is bounded and 0 capital T, so you see that the maximum attains in the on omega t closure, is it not? So but what it says, that maximum principle says that maximum of U over omega t closure, this will attain as maximum of U of gamma t in the parabolic boundary. Okay, and similarly I can think of, so why it is possible if my U solves the heat equation. So if U solves the heat equation in omega t, then this is the case. Okay, so again we can consider maximum by maximum replaced by minimum. So minimum of U over omega t closure, is minimum of u over gamma t. Okay, so before discussing these things, let us try to consider one example and then see what happens. So now I'm considering this function u xt, which is 1 minus x square minus 2t. So my omega is 0, 1 cross 0 to capital T. Okay, so this is my, that means my omega. Okay, so I have to put omega t in this case. So omega is my 0 to 1. So now you see that u solves the heat equation. In omega t. Okay, because you see that ut, which is nothing but minus 2, and uxx, this is actually is equal to again minus 2. That means ut minus Laplace u is equal to 0 in my omega t. Okay. Okay, and also you see that this is a polynomial, so then it is basically it is a smooth, so this is CT1 omega t intersection C of omega t closure. Is it not? So u belongs to C21 omega t intersection C over omega t closure. It holds. So now if my xt belongs to omega bar cos 0 of t, which is basically omega t closure, then what you have seen that 1 minus x square minus 2t, this is less than equal to 1, always true, and equality holds if and only if that my x should be 0 and t should be 0. Is it not? So that means that maximum of u over this omega t closure, this is actually my u of 0, 0, and that 0, 0, this is actually your parabolic boundary gamma t.
So how did we get that inequality less than equal to 1?
This is minus x square minus 2t. Okay, x lies between 0 to 1 and t lies between your 0 to capital T. This is negative, no? Minus x square minus 2 to t is positive or greater equal to 0. So this is always less equal to 1, no? Because you are subtracting, no? 1 minus something.
Okay.
So this is always less equal to 1. And equality holds if and only if x is equal to 0 and t is equal to 0. Is it not? Okay, so and then this is 0, 0 point. This is on my gamma t. Okay, this is on the parabolic boundary. So maximum attends in that case. So not only that, I told you that the result should be true for minimum case also if you solve your heat equation. So now what is your minimum point here? So again, if your xt is in my omega t closure in this case, then I can say 1 minus x square minus 2t, sorry, 2 of small t. This is always greater than equal to minus 2 of capital T, no? This is always the case. And hence, because x lies between 0 to 1, and the equality holds if and only if my x should be 1, so that's is equal to 0, and small t is equal to capital T. Okay, so this implies my minimum over omega t closure of u, this is actually minus 2 of t, which is u of 1 and capital T. So now you see that 1 and 1 and capital T I have. Okay, but capital T I have there, but your capital T is not in a parabolic boundary, no? One is there, small t, but not in a parabolic boundary. So I think here we cannot say the minimum holds here. Okay. So only I think that maximum of u omega t closure is equal to maximum of u tau of t. At least in this case, it says that the minimum of u attains at 1 and capital T point, but 1 and capital T is not in my parabolic boundary. So we cannot say that here the minimum principle holds for heat equation. Okay, so what my statement previously I said that maybe this should be replaced by minimum, but this is not the case, I think. Okay. Okay. But let me tell you why this is the case. I have 0 to capital T, minimum of T equal to holds. Okay. Anyway, this is on 1t, but 1t does not belongs to my gamma t, because 1 is del omega, but then capital T I have. Okay, so these things actually, this is sub example, but we can generalize it, that is given by the maximum principle. So I don't know the theory, I'm not going to prove these things. Again, proof is like in a previous case how we have done it for parabolic for the elliptic case. So for the proof, if we, as I told you, just look at the lecture note by Professor Srinath in his web page, you can find out. Okay, so I have not put it there, or you can look at also the Evans book. So proof is there. So what it says that, so let U, which is C21 omega t intersection C over omega t closure, which solves the heat equation in omega t. Then the two conclusions I can have, that maximum over u over omega t closure, which is maximum over u over omega t. And second is that, so for the elliptic case, we have seen that if u is connected, and if I have a point which is in the interior point, then it is constant, no? But here it should be a constant, but you will see that depending on the time point. So what I try to say, that furthermore, if omega is connected and there exists a interior point, say point say x0 t0 is in my omega t, such that the maximum attached at the interior point, that means u of x0 t0, which is maximum over u over omega t closure, then what is the conclusion? Then u is constant in omega t0 closure. Okay, u is constant there, but not, so above t0 we cannot say. So what is your omega t0? This is nothing but that omega closure cos 0 to t0. So now if you look at this picture here, so now this is my t0 point, so it includes t0, but below here, okay, so this is t0. So in this domain the u is constant, but we cannot say anything else about here. Okay, we cannot say anything else about here. So what it says, that it is constant in omega t0 closure. Okay. So as a corollary, what I can say is the following, that let u be, this is my C21 of omega t closure, omega t, and solves the heat equation ut minus Laplace u is equal to 0 in omega t. So now if u is less equal to v on the parabolic boundary gamma t, then what I can say, then u is less equal to v in omega t. It's kind of comparison, because if u is less than or equal to v on gamma t, then u less equal to v on gamma t. Okay, because you can see from just here, because if you look at u minus v, it is also satisfy your heat equation, and on the boundary this is negative, and hence u minus v is less than or equal to maximum of u minus v, and that is equal to 0, so u less equal to v in omega t. That is the comparison test for that. Okay, so let us consider one example, so that we can use this comparison type of principle to find out the following. So what I consider, say omega, in this case my 0 to pi I am considering, and t greater than 0, which is fixed. Okay, so now I am considering the solution, the ut minus u one dimensional, ut is equal to 0 in my omega t, and u of 0t, which is equal to 0, is equal to u of pi over t for all t belongs to 0 to capital T. Okay, so this PD is given to you, and not only that, I am giving the initial condition u of x0, which is sine square over x for all x belongs to my omega closure. Okay, so it is given to you. So my claim, or so that u is positive, and not only that, this is less than or equal to e to the power minus t of sine x for all x belongs to 0 pi cos omega t, or 0 to t. Okay, so in particular I have to show that u is non-negative, and u of xt less than or equal to e to the power minus t sine x. So if I try to construct Vt, which is actually e to the power minus t sine of x, okay, just looking at these expressions, v of xt. So if I show that vxt also satisfy this heat equation, okay, because it's all are in the bounded domain and so on, and then in the initial condition, sorry, in the parabolic boundary, if my u is less equal to v, then from my comparison principle I can conclude that u of xt less equal to but minus t sine of x dx. Okay, so let us do that things. So let v xt, this is e to the power minus t sine x. Okay, if you consider it, then again you see that v satisfies my heat equation in omega t. Whatever we define this omega t, in this case it satisfies your heat equations. Okay, so now what is your v over 0t sine 0 is equal to 0? So it is 0, and if I consider that x is equal to pi, that sine of pi, that is again 0, so this is actually 0, is it not? So v of 0t is equal to 0 and is equal to u of pi t. Okay, this part I have. So you see that this is again in this case, if my x is in omega, okay, x is in 0 to small pi, then what I have v of x of 0. So this case, actually this is nothing but sine of x, okay, and hence what I have, v is greater or equal to 0 on my parabolic boundary gamma. Is it not? Okay, so you notice that I have my sine square x, okay, which is for u of x is equal to sine square x on my omega closure, and then this is less than equal to sine of x, okay, on the interval 0 to pi, which is my omega closure, is it not? So this implies my u is less than equal to v on my parabolic boundary gamma t. Okay, so hence by comparison principle, I can say that u is less equal to v, okay, which is in my omega t, that is I want. So 0 less equal to vxt less than or equal to e to the power minus t sin x for all xt is in 0 pi to 0 t. Okay, so by using the comparison principle, we are having that part. Okay, so okay, so like in exercise we have given you for the heat equation for the elliptic equations, that I can think of some kind of sub-solutions of the heat equation, super solution of the heat equations. So here is the following definitions I am making, that V belongs to C12 of omega t is called a sub-solution of the heat equation if Vt minus Laplace b is less equal to 0 in omega t, and we call it the super solution if this is greater than equal to 0 in omega t. Okay, so sub solutions and super solution. So if it is a sub solutions and super solution, then it is like subharmonic and then super harmonic. Then we have said that if it is harmonic, if it is both subharmonic and super harmonic. So in the same way, we can say like this. So using this definition, so you can just check it yourself that if we consider say phi, which is from R to R, say suppose smooth and convex, actually C2 is enough in this case, then you see that if we consider my V, which is P of U, okay, so then V is a sub-solution of the heat equation if U solves the heat equation. Okay, so I can know that if I know a sub-solution, I can make many sub-solutions of the heat equations. So not only that, if I consider V, which is my du square plus ut square, then V is again a sub-solution. Sub-solutions of heat equation. Okay, in omega t, so provided U is a solution of the heat equation. Okay, just nothing else, you just look at now, because as I say that V is smooth and so on, and for this case you just try to find out what will be your Vt and then the Laplace of V, and then use the property that V is convex and so on. So the second derivative is critical to 0. So from there you will see that V satisfy your the inequality Vt minus Laplace V less equal to 0 in omega t. So in other words, V is a subsolution to this heat equations. Okay, so in elliptic case, using maximum principle, we have proved uniqueness of heat equations, is it not? So here we also try to write down the uniqueness principle. So there also we have done two ways. One is called the energy method, another is using the maximum principle. So here also we'll do it the same thing else. So that is uniqueness on bounded domain. What I say is that, so let G, which is C of the gamma t, this is continuous functions on my parabolic boundary, and f is given to you, it is continuous on omega t, then there exists at most one solution u, which is C to 1 omega t intersection C over omega t closure of the initial boundary value problem, the PDE, that ut minus Laplace u is equal to f in omega t, then u is equal to g on gamma t. Okay, u is equal to g on gamma t. So from there I can conclude how to prove it. Basically, suppose you have a solution, two solutions, u1 minus u1 and u2, which satisfies my this problem. Then what I can write down, that if we consider say V, which is equal to u1 minus u2, then V satisfies your heat equation. So if you have a u1 and u2, say consider V is equal to your u1 minus u2, then Vt minus Laplace V is equal to 0, and in omega t, then V is equal to 0 on gamma t, is it not? So from there actually what I can say using the maximum principle, that V is less equal to 0. Okay, so now again I consider say W, which is equal to u2 minus u1. So then again I can say that W satisfies the same equation, Wt minus Laplace of W is equal to 0 in omega t, W is equal to 0 on tau t. Again by using maximum principle, that W is less equal to 0, that is ut less equal to u1, and from here I have u1 less equal to u2. So from, if you just combine these two things, what I have, u1 is equal to u2 in omega t. Okay, so this is unique. So moreover, I can use the energy method to get uniqueness of solution. So another method, that is called the energy method. So what is this? Energy method means, for previous case, we define that the integral over gradient of W square and so on. So here I am defining say Et, which is equal to integral over omega your W square xt say dx, where 0 less equal to t less equal to capital T. What is your W? W is nothing but your, suppose I have two solutions, which is u1 minus u2. Okay, so then already you have seen that W satisfy my heat equations, and W this satisfy these equations, no? Okay, or maybe I can put V, because this one I put it. So then what if I differentiate with respect to t, then what I have e prime t. Okay, so if you see that e of 0, this is nothing but actually 0, is it not? E of 0, this should be nothing but 0. Okay. So now what I am having that e prime t, this is nothing but 2 times integral over omega. This is v and then vt of dx. So now vt is equal to Laplace of v. So then this is 2 integral over omega v Laplace of v of dx. So now if you do the integration by parts formula, so then what I have, this is minus 2 times integral omega, you get v square of dx, because there is no boundary term, is it not? Because for the boundary actually it gives you 0. So what I have here, that this is less than or equal to 0. So what I have, e prime t is less equal to 0 for all t greater equal to 0 and okay, so less than or equal to t. So this implies that means e is decreasing, hence et is less than or equal to u of 0. U of 0 is equal to 0. So that means what? E of t is equal to 0. So if you look at my definitions, so this is non-negative, no? So that means inside thing is equal to 0. So v of xt identically 0. Okay, because v is continuous and so on. So that is u1 is equal to ut in omega t. This holds for all t. So this is u1 is equal to ut in omega t. So what it says there, by using this is called the energy method, you can also prove the uniqueness of the solutions to this parabolic problem. Okay, so I need the bounded domain, that is more important, because without bounded domain we cannot have uniqueness. So here we are not ensuring that whether solution exists or not. What we are saying that if solution exists, then solution should be unique. Okay. Okay, so let us consider one example where we can use uniqueness to say something about the solution. So now I consider the IVP in this way. So ut minus uxx is equal to 0, say 0 less than x less than 1, t is positive, and then we have finite t. Okay, capital, some capital T is there. So maybe I can say 0 less equal to 1. Okay, this is what I have. And then u of x of 0, which is equal to 4x into 1 minus x, for 0 into x less equal to 1, and then u of 0t, which is equal to 0 is equal to u of 1 and t. Okay, boundary value problem for t is positive and also less than equal to t. For all t is in 0 to t. You can see for all t belongs to 0 to capital T. Okay, so now my claim is the following. Then u of xt, which is equal to u of 1 minus x times t for all x belongs to omega t, closer maybe. Okay, so how to prove it for that? So if I know that if I define my v of xt, which is equal to u of 1 minus xt, and suppose you solve this problem, okay, then if I show that v is also solution to this problem, then by uniqueness I can say that u of xt is equal to v of xt, and in other words u of xt is equal to v of 1 minus xt. Okay, this is the concept. So I am considering v of, so let v of xt is equal to u of 1 minus x times t. So I need to check that v satisfies my this equation. So since u is in C2 and so on, so the regularity things is fine. There is absolutely no problem. Okay, so now you check yourself that, okay, so in this case, what is my Vt? This is nothing but your ut over 1 minus x comma t. And then if you have v of x, which is should be minus ux of 1 minus x comma t, and v over xx, this is again u over xx of 1 minus x comma t. So this implies that vt over xt minus vxx over xt, this is same as over ut over 1 minus x comma t minus uxx of 1 minus x comma t. Okay, so this is actually 0, because 1 minus x lies between 0 to 1, So 1 minus x is like between 0 to 1. So then it is some domain, say y ut yt minus uxx of yt is equal to 0 because you solves this problem. So you see that it satisfies the given PDE, and not only that, you need to check it that these conditions hold. So now if you look at here also, then you will get the same thing else, because if you replaced x by 1 minus x, how the conditions is given here, then this is true. Okay, so v of x0 is equal to 4x into 1 minus x, because that should be 1 minus x. So if you put u of 1 minus x0, that is again same as 4x of 1 minus x. That is how we have choose it in this way. Okay, and so on. So this 4 is just the, I have given some number. There is, you can put 2, 3, and it does not matter. So v satisfies all the conditions. So hence by uniqueness, what I can say that v of xt is equal to u of xt in omega t. That is u of 1 minus x comma t is equal to u of xt. So this is actually I want to show it in omega t. Okay. Okay. So these are the uniqueness things for the bounded domain. But for unbounded domain, or if I look at, say, the Cauchy problem, then can I have the uniqueness for the Cauchy problem or not? So now you see that for the previous one, for uniqueness, you are using the maximum principle. That means I need to understand whether the maximum principle for Cauchy problem holds or not. But in general, it cannot be true because it is in unbounded domain. So that means you need to impose some conditions as mod x goes to infinity. Is it not? Or some growth estimates we have to look at. So I'm writing down the maximum principle for the Cauchy problem as a theorem. And then I will put the uniqueness of the Cauchy problem, and then I will stop it. So next day I will talk about so-called the separation of variable by using Fourier method. Okay, so what it says that, so let u, which is C21, say Rn cross 0 to t intersection Cn of Rn cos 0 to t. Okay, so you can think of the boundary of this in this way, and it solves the heat equation ut minus Laplace of u is equal to 0 in Rn cross 0 to open t, and u is equal to g on Rn. Okay, that means Rn cross t is equal to 0. And this set. Not only that, and it satisfies the following growth condition. So this growth condition is important. U of xt, this is less than equal to capital A times e to the power a of mod x square. So where x is in my Rn, 0 less equal to t less equal to t, for some constant capital A n positive. Okay, so if the solution to this problem, so it solves this heat equation. Not only that, it has a growth condition like this: u of xt less than equal to a times e to the power a of mod x square, or you can consider the modulus because this is no matter, it is a positive. Okay, for constant a is positive, then what I can say, then supremum over Rn cos 0 to t of u, this is should be same as supremum over Rn of g. because g is a function of x. So here we are not writing down as a maximum because we don't know whether the maximum will attain or not. If the supremum may attain at some point, then it is a maximum. No? So because it is unbounded domain, so we can talk about always the supremum but not the maximum. So that's the only reason that we have proved it here. So what it says that you consider the Cauchy problem. Okay, you consider the initial value problem on a whole domain Rn. Then the supremum of u over Rn cos 0 to t is given with the supremum of Rn of g. But extra conditions I need that u xt, it should satisfy the following growth condition. Okay, so under this growth conditions, I am having this result, that supremum over u of u over Rn cos 0 to t is equal to supremum over g over Rn. Okay, so as a consequence of this maximum principle for the Cauchy problem, I will have again the uniqueness of Cauchy problem under some growth conditions. So I put as a corollary, which is uniqueness of Cauchy problem. So what it says that, so now again you consider this equation ut minus Laplace of u is equal to 0. Sorry, I don't need 0. G f in Rn cos 0 to t and u is equal to g on Rn cos t is equal to 0. So what I need my conditions f, it should be continuous. Okay, Rn cos 0 to capital T, and g is also I need continuous functions in Rn. And suppose, so then what I am saying, then there exists at most one solution u which belongs to C21 Rn cos 0 to t intersection C over Rn cos 0 to t, this is closed interval 0 to t, having the growth estimate exactly whatever we wrote down, u over xt is less than equal to a times e to the power mod a x square. Okay, for some constant a is positive. Okay, so this is the growth under these growth conditions. What we try to say that if you want that existence of this problem which is having the growth conditions in this way, then it is unique. So it is coming from your the maximum principle for the Cauchy problem, because suppose you have two solutions u1 u1 minus u2 and so on, and then u1 also satisfy these equations, u2 also satisfy these equations. So now if you look at say w which is equal to 1 minus u2, then u2 minus Laplace is equal to 0 and w is equal to 0 on Rn cos t is equal to 0. And not only that, so now since u1 xt less equal to this part, ut of this, so w is also less than equal to some another constant, maybe a1 e to the power a of mod x square form. Is it not? So then using this maximum principle, what I can that supremum over w over Rn cos 0 to t, this is actually is equal to 0 because g is equal to 0. So in other words, u is less equal to 0. So now again similarly you can consider say the with minus sign. Okay, so means you apply this is plus minus u1 minus u2. Okay, So then also you can have that. So initially you have u1 minus u2 less equal to 0, u1 u2 less equal to 0. So hence we have the uniqueness. Okay, so I stopped here now. So in the next class I will talk about, so can I find a explicit solutions for the problem, suppose in a bounded domain, and also we look at the one-dimensional case, okay, using the separation of variable. So that means it is t and x. So I try to look the solution in this form: u of xt is equal to some, say, a of x and b of t, where a and b are function of t, and then using the Fourier coefficient. So for that case I try to look at the boundary conditions, so that is continuous and so on. So from there we try to use the Fourier method to find out the explicit solution for the problem. Okay, so I'll stop now, and then the remaining two class I'll start wave equations. Okay, I will not cover the whole things, but whatever I can cover it, so I'll try to do it. Okay.